Hello, I'm Nick Psaki, and welcome to the AIACross Federal IT Newscast of the Modern Data Experience. I am Nick Psaki, Principal Technologist with Pure Storage, and I'm joined today by Dr. Michael Segala with SFL Scientific. Thank you for joining us, Michael.
Hi, Nick. Thank you for having me.
So, Michael, the recurring theme of the Modern Data Experience has really revolved around artificial intelligence and machine learning operations, and those efforts inside the federal government. So I guess I want to begin with, why don't you tell us a little bit about yourself and a little bit about SFL Scientific?
Sure. I will start with one or two sentences on SFL, then I can kind of back that up and tell you kind of how we got to where we are today. So I run a company called SFL Scientific. We are a data science consulting company. And like you mentioned, right, our job is to really build out artificial intelligence solutions for our customers. And clients normally come to us when they're trying to solve hard R&D problems. And we'll talk very specifically what that means, because it doesn't mean you're just sitting at a lab bench pipetting in chemistry, but fundamentally trying to build something novel that will be integrated into a technology. Or they come to us when they already have that technology stack done, and they're trying to embed AI into that for a fielded kind of testing or infrastructure or commercialization. And we will bring our expertise from everything from fundamental strategy. How do we think about the data? How do we think about AI? How do we think about people, governance, security, all that stuff from a strategy perspective, to the data architecture to actually support AI. And then always, right, our core thing that we love to do is anything around bespoke algorithm development. And that's really what SFL gets involved in. So we can talk about that in a few minutes, but kind of how we got here. So I did a PhD in particle physics about a decade and a half ago already, kind of dating myself. I feel like it wasn't that long ago, but I guess it was. Back when kind of the field of data science was really starting to emerge out of academia into the commercial realm. So I was very fortunate to be part of a team that was at the Large Hadron Collider doing really large scale petabyte kind of analysis that is now kind of traditional machine learning. We did a bunch of stuff. We found some particles. We won a Nobel Prize, all that kind of cool stuff, which basically set us up for the understanding of how do you solve big, hard data problems that need really, really interesting algorithms to solve and sift through a whole bunch of stuff. So that's kind of where I come from. And then basically got out of school, started the company with this idea of how do we take our scientific knowledge and apply that into both the commercial and the federal space, which is what SFL does now.
Fantastic. The federal government's been on a large, broad, and wide effort, deep effort to leverage artificial intelligence and machine learning across a vast range of problem spaces that are not dissimilar to what everybody else is trying to do as well. Everything from computer vision to logistical supply chain analysis, failure analysis, predictive analytics, predictive maintenance, and things of that nature. So into that realm, SFL Scientific moves to provide expertise on how to most effectively leverage that. But tell us a little bit about the evolution of the services that you've developed, because a lot of times that sort of gets shaped by what is it that the customer is trying to do. So you mentioned that you've been brought in to solve some interesting problems or help your customers in the government address those problems. Either they already have an architecture, or they already have a data set, or they have a notion about what they're trying to do. The advisory services that you guys have provided, how's that evolved over time?
Yeah, it's a great question, because the evolution is actually quite interesting. So back in, let's call it 2015, 2016, where this new evolution of AI has started, we really were brought in back then for POC around, can we prove out a very, very small sliver of technical feasibility? This could be, I have some images, what's in those images, right? It could be geospatial. Can I identify a house and draw a box around that house? And it was so non-ready for productionization. It had no architecture around it. It had no real ROI. It had no people doing it outside of what I'm going to call a science experiment, meaning a bunch of folks sitting around seeing, can I do something? And a lot of AI, still now, but especially back then, that was successful. Can we take some images? Can we take some text? Can we take a couple signals? And can we detect something better than what the current kind of humans or traditional analytics or statistical analysis was able to do? And that's really where, if you think about 2015, 16, 17, 18, that's where a lot of the stuff really lived. Then what has happened slowly, and we are still, in my mind, very, very early in this evolution, you start to see a few big wins. And the big wins have come from a couple of the big key commercial players in the space. You get folks like the Googles, the Teslas, the Amazons, the Facebook, starting to showcase in their marketing material that they're getting huge leaps in performance of, it could be anything from optimization of algorithms around ads to, autonomous vehicles. But they're starting to say, we're doing this, we're completely pivoting our industry, and we're doing it through AI. And all of a sudden, people start saying, oh, maybe this isn't just a cool little tool that we should put away in the, the corner and let the geeky people work on, but maybe we should start really integrating this into our stuff. So roughly 2018-ish, you start to see this evolution of people saying, I'm going to embed AI, not just as kind of a one-off use case thought, but starting to say, how do I build holistic strategies from the C-suite downwards, where we're going to say, well, how do we support this? And we need to support this from our data infrastructure perspective, and from a monetization perspective, and from an IT and a hiring and all these things. So as the evolution in the last few years went from single, very isolated use cases, you're now starting to see the proliferation of the productionization of these use cases. And that's still, again, very much in its infancy. A lot of people like to talk about AI and how great it is, but very, very few people are actually making money on it yet. There's obviously a couple of big players that have, but people are still very, very new to this space. And that's, along with us, the evolution that we've taken as well. So as we've kind of grown with these organizations, our services have really expanded from just thinking about the algorithms as kind of, the 90% of everything we did, to now that's often the smallest stuff that what we do. Because it's all the stuff about how do we think about getting stuff to the algorithm, and then how do we take that algorithm and go deploy it somewhere. So it's all the pre and the post, and it's not just technology, the data, the people, the infrastructure to support it, right? Those three levers are incredibly complex, and they all require their own thought processes and change management. And that's how we've had to naturally evolve as the industry is getting some legs under it and people are getting their wins. So yeah, I mean, I hope that answers your question, but that's kind of how we have seen the evolution here.
It begs a couple others, as they always do. So from your perspective, where have you seen some key wins, particularly in the government space? Not naming names, of course, but as you said, a lot of this started really moving forward quickly in 15 or 16. And I kind of, in my past, referred to these as, it's a kid's soccer game. Mm-hmm. Everybody swarmed the ball. Yep. And, eventually as it matures and evolves, the discipline around playing the game becomes people are at their positions, the ball moves around, it starts to look like a more structured effort. So we've gotten to the point now where the evolution of AI practices, AI and machine learning operations and so forth have gotten us to the point where we've actually been able to deliver some wins. And I'd love it if you could sort of showcase some of those from your perspective. What have you seen? How have your customers been successful?
Yep. So I think we can draw a pretty gray but clear-ish line between the types of use cases out there. And there's really, right, you can bucket them into two, and there's thousands, yep, but let's be naive and say there's two. And I'm not going to focus on the first category. So the first category I'm going to say is operational use cases, back of the shop use cases, enhancements over RPA and ERP systems. And that alone, you could solve trillions of dollars worth of problems with, and you can revolutionize probably every agency in the world, right? And I don't want to touch it because honestly, that's not where we sit in our core strength there. And there's some companies out there that dominate and do a really good job at that space. Where I'm more focused, and I can talk a little bit more intelligently about, is the spaces that are truly augmenting the operator, augmenting the battle space, augmenting the analyst or the medic or whomever is actually needing to make some kind of real-time tactical decision. And that's where we see significant, not just spending, but willingness to adopt technology. One of the biggest challenges that we see, obviously, in any space, in the commercial space and the federal space, but mainly in the federal space as well, is to take a new technology injects significant risk into the process. And when you're standing up the F-35 program, or you have soldiers in the field, or you're in charge of trillions of dollars, any new risk obviously can't just get thrown willy-nilly and they say, okay, go do it, right? So we have to be very, very thoughtful and rigorous around that. And that precludes us from moving very quickly in the government space very often. So you have to say, well, where are there areas that people have overcome some of this and have more of a tolerance to innovate? And you see that, right, in places like the Special Forces or NGA or Army, Navy in some areas, obviously like NAVAIR, NAVSEA, the war centers. They are very much interested in saying, what can we take early TRL 4, 5, 6, really start doing innovation, and then building that into a program of record. So you start to say, these types of solutions that are going to be, how do I augment the operator, right? Somebody's in the field and how do I make them take the cognitive load off of themselves? That's where we're starting to see a lot of success. A simple example that's probably one of the most prolific is probably with the NGA, right? The NGA, if you're an analyst, what do? You sit and stare at incredibly complex geospatial images, where if you're one analyst, it might take you 24 hours to completely go through and look at one cityscape of, wherever you're looking, a couple square miles. That's a completely arduous task. And now they say, well, how does it change day to day, hour to hour, minute to minute? Well, you can't do that if you're a human. But you can do that if you're an autonomous system and you understand deep learning and you can throw it and automatically do change detection. So that pivot from a whole bunch of humans needing to make a lot of really rigorous decisions to augmenting that human to make real-time decisions at the same tolerance level of, getting things right and wrong, that's where you're going to see a lot of really quick adoption. And you do, right? So you start to see that in NGA and Army, Navy, like we've talked about. And just to kind of drone on a few more seconds here, if you look at a lot of the kind of early stage work that comes out in the CIBRs or the BAAs and things like that, you'll start to see these agencies are calling for this innovation very specifically to augment the way that their current people do things. And that's where I think the technology is being incredibly impactful, and that's where we see it as well.
Artificial intelligence augmentation has really been the easy on-ramp and the most accessible on-ramp to the adoption of artificial intelligence, not just in the DoD, but widely. How do we use AI to do exactly what you said, which is enable human capacity? Basically, it's buying time back, buying thought space and bandwidth back into a person's activity or in their day, helping them be more productive. I was really excited to see that. Being a recovering geospatial analyst, it seemed a natural fit. What do you see in terms of adaptability of algorithms from one endeavor to another? One of the things that I often said was, computationally, doing a computer vision analysis of the pathology of cancer on cancer slides. One entity or agency I'm aware of scans slides, like microscope slides, and they're 9 gigapixel images. Well, as a geospatial analyst, when you said that number, you have my undivided attention. So you're looking at a 9 gigapixel digital image of cancer and the pathology of that cancer over time. I went, sounds like coherent change detection to me. Well, computationally, that's exactly the same thing as the process you just described of an analyst looking at terrain and terrain features from overhead and watching the evolution of those changes over a period of time, the histography of the geography, as it were. But do you see a lot of that mobility or portability of algorithms and models from one application to another?
So yes, but let's caveat that strongly.
Always caveats.
So we work our two biggest spaces are medical imaging and DoD. So I can talk very much around the applications of digital pathology or histopathology and how absurdly similar it is if you're doing NGA geospatial differencing.
Computationally, it's the same thing.
Same thing, algorithmically, same thing, all that stuff. Where it becomes incredibly complicated is how do you deal with the nuances in the data itself?
Right.
So in reality, if you think about the world from a data perspective, we have only a couple data sources, right? We have images. I don't care if it's video. I don't care if it's thermal. I don't care if it's optical, whatever. We have images. We have signals from a signal processing perspective, right? This could be Fourier transforms. This could be whatever, right? This could be financial data for all I care, or we have text, right? That's really all you got. To solve those 3 different modalities, you only have a few different algorithms that do it, right? Like the couple deep learning things over here, you have your XGBoost over here, you have a couple different permutations. So from that perspective, there's really not much that has to be treated algorithmically. The hardest part, and one of the things we can talk about as we move forward in this conversation, is we're starting to get to the point where we are no longer necessarily computationally limited. And we are getting to the point where the algorithms are so big and robust, they can really start to solve a lot of the core problems that we're at. The biggest challenge that we see of adaptability of algorithms is how do we create representative data sets that will translate and generalize to the actual robust environments for productionization. A good example of this is, let's take the geospatial imaging. If I were to build an incredibly complex classifier for buildings in the Middle East, which are only 1 or 2 stories high, and they have a very similar kind of landscape that you're expecting, and if I took that kind of trained model and applied that to, for instance, somewhere in France, where you now have 40 or 50-story buildings, the angle of aperture is changing, everything is a little bit different, those no longer are portable. So even though you're doing the same task, the environment and the conditions of that task and the data have changed significantly, whereas the algorithms don't necessarily apply. So what you're going to have to do is think very hard about, how do I treat the data such that I can actually use the same kind of backbone from an architecture perspective, but really treat the data as a first-class citizen instead of the algorithm as the first-class citizen. So from that point of view, you get into a lot of interesting conversations around what will be the next leap forward in kind of accuracy or precision type of ability, right? How do we make that better? And I'm on the incredibly strong perspective, and this is by no means my only my perspective alone, that without a very clear data strategy first and foremost, you're always going to be limited by how well the algorithms play. So we have to think about very strongly, how do we create robust data scenarios? How do we start thinking about synthetic data? How do we think about augmentation of those data assets? And that usually isn't necessarily transferable from histopathology to NGA. Right? All that is going to be so incredibly unique to that exact domain, where the learnings could be same, but you're not going to just say, okay, I did it over here, let me lift and shift it over here. So that's where the big differences lie, not in necessarily the algorithms. So a long-winded way to say that, but I hope that kind of
no, I mean,
knows where I was coming from.
You know what, the reason why is always the important part, right? And it saves you from doing something that you think's going to work, but doesn't deliver the results you were necessarily looking for, and then teaches you, oh, wow, I have a whole lot of work to do, or I've got a whole lot of training to do.
That's right.
So obviously, you said something earlier and touched on it again in context of your last point, that you're moving a lot of data. Obviously, I love data. That's why I do what I do. Yep. And data infrastructure and the way in which data moves in these systems has really challenged everybody, because artificial intelligence training and AI and ML ops require data service that has an extraordinary level of agility and performance. How have you seen architectures for the data architectures themselves evolve in the last 7 to 10 years, from where we were with a single workstation with an NVIDIA Titan card in it to actually purpose-built infrastructure for doing AI and machine learning operations? How have you seen that move from the start point to today?
Yep. So I'll answer that, but then I'll also layer on what's our next big challenge. So yes, the evolution has been pretty significant, right? There's a few things that have really enabled us over the last decade. It's data, more representation of data, right? So the data side, the algorithm stuff, and then the infrastructure to support it, right? Like if I want to solve drug discovery, pathology, NGA 5 years ago, well, I'd wait 6 years and I'd say, okay, I'm bored now, I'm going to move on to something else. But now, like I literally have an ARI sitting in next door to me, and I can just run it up, and I can solve incredibly complex chemical structures overnight, come back and be like, ooh, I found something novel. So you're starting to see obviously this evolution very strongly, where the barrier to entry now is extremely low. There is no excuse, with a couple dollars and a couple people that know what they're doing, that you can't start doing very novel things. It doesn't have to be novel in the terms of you're solving the world, but novel in the sense that you've augmented a workflow within your environment that nobody else has augmented before, whatever that happens to be for a specific organization. So from a transitioning perspective, a lot of people for a long time said, well, I don't have the GPU cards, the CPU, the FPGA, whatever it is that they need to solve. That's no longer, in my opinion, a big barrier. You could go out and buy these things. You can go to Pure Storage. You can go to Amazon. You can do whatever you have to do to get your hands on these things. These things exist. They're readily available. And frankly, there's enough horsepower out there today for not a significant amount of money that you could probably solve 99% of all the problem spaces in the world. Sure, there's always going to be that 1%, but frankly, unless you're very early academics, you're really not doing that, or you're a Google brain or something. So let's not ignore those. So that exists. And that's great, because that opens us up to solving a lot of hard problems. The challenge now is, as we start solving problems, just like we were back in 2015, 2016, when I started this conversation, we've now gotten to the place where we can start doing more feasibility. We can say, well, I don't want to just solve that geospatial image offline. I want to now start embedding that into an autonomous drone or a ground vehicle or a submersible vehicle, and actually start doing it directly on the device itself. And that's really where the next evolution, and where frankly, we spend a significant amount of our time. Now we're in another world of problems, because what happens is we usually have our big supercomputer sitting behind us, and we're having fun, and we're experimenting, we're training our models, and we're proving, oh, I can do real-time detection of, I don't know, whatever, chemical warfare and things like that, which is a problem we work on, so I'll talk about. You can do that. And then you say, well, how do I take those models, and now how do I put them in an incredibly low swap environment on a drone with at best, a Jetson, with degraded data feeds and no storage, and just say, now go be as performant. That's incredibly hard. And the biggest limiting factor of those use cases now, again, is infrastructure. It's just a much smaller infrastructure, right? So we're turning the crank now, right? And now we have to get to this next evolution.
So we're involved, obviously, with a lot of folks who are doing autonomous locomotion. It could be for cars, it could be for airplanes, it could be for boats. And what you said is actually the hardest part. I mean, if you have, if you've got a research supercluster that's doing simulations of driving through the city streets of the world, that's great. You've got a research supercluster behind you. Right. But once that model is trained, you're deploying it into something that is a car, and that's all the infrastructure you have. That's kind of the exciting part, is transitioning from development into deployment. And the thing that I often remind people of is that training artificial intelligence is a lot like training anything else. All right. You go through school, you go from kindergarten to high school, college, postgrad, doctorate, postdoctorate. All along the while, you're getting better and better at what you do. And then you go out into the world and you actually do something for a living, right? Yep. Or training soldiers. They start off day zero, they're people on the street. 16 weeks later, you've got to send them somewhere in the world to do the job that you sent them to do. Well, developing algorithms, we do it in order to deploy them. But like you said, making a deployable model or a deployable algorithm, that's kind of the hard part. I kind of almost think of it as a deployable entity. And then do you retrain it? Well, you can't retrain the algorithm that's already working. Of course, they are pretty adaptable. But if you want to train a new model, then you have to be training a new model, preferably against updated data, so that you get a better model. So this is kind of all a really fascinating thing. We do the same thing with people. And I'm not sure that people involved in, or who are consumers of artificial intelligence, realize that there are a lot of similarities. Cognition is cognition, whether it's, carbon-based or silicon-based. The learning is continually in progress. So it's kind of exciting. Have you seen, growth or adaptation of existing models to updated problem sets, or seen them evolve over time and new versions deployed into, I could say operational environments or applicable environments, because obviously biomedical, we're just talking about into the domain that they've been deployed in. Are you seeing iterative improvement in faster periods of time?
I want to say, because I want everybody to feel good about themselves, yes. In reality, very few people are truly doing this. Okay. Yet, especially in the DoD. So I think we're going through that life cycle now, where there's obviously people, there's pockets of people that are doing this. Obviously, I'm not saying that there's not, but the bulk is still not yet there, right? The bulk is still doing early TRL test and evaluation to see first and foremost baseline principles. Does this thing work? Now, the bulk over here, the more advanced folks, right? Especially in the DoD. In the commercial, this is a little bit more prevalent. Obviously, the Teslas of the world, sure, they're doing this all the time. But in the DoD or whomever else, especially in the medical device space, which is incredibly hard because you get into FDA and then the update policies. It's not like you just retrain and deploy and say, go, right? Like the test and evaluation process here, in my mind, is one of the most fascinating topics of how do you truly test an algorithm in a new environment that you haven't been yet in and you don't have data yet to represent. It's very hard. So we can put that to the side in a second. But we do see some folks starting to take that leap of deploying a technology and then having a rigorous kind of testing scenario and testing plan to say, when has my data or my model moved significantly enough that we need to capture a net new environment and then use that to retrain? So we can use that simple example I gave of, the geospatial of, I was once now in Mosul and now I'm in Beirut and the entire cityscape has changed, which I know by definition it does, right? So you need to be very thoughtful about that. And there are some organizations out there that have instilled these principles of saying, what is the fundamental change in data architect, data type itself, and how do we monitor these shifts autonomously to say something necessarily has changed, and here's the statistical test that I'm going to do to show that it has changed, and here's the statistics that I need to improve upon such that I can recapture the accuracy that I was going for. So you're starting to see this, and you're seeing some workflows and some kind of thought papers out there on how to do this, especially in autonomous systems, because that's incredibly hard as well. But the bulk of the DoD itself is, in my opinion, and again, I'm a novice in a lot of things, it's not yet there, which is okay, which means we can set the paradigms and the principles to help them get there and then show them, here is this kind of evolution, right? This scientific method of how you go about it, such that when you are ready and you are deploying and you are actually testing in the field or deploying in the field, this is what you need to do. And this is how you're going to go through this iteration cycle.
I mean, as you said, a lot of this is early, but it gives us the opportunity to create the processes for moving forward. We know that we're going to have to do it. So it's good to be able to think our way forward and develop those frameworks for iterative improvement over time. You work in a really interesting spot, being between life sciences and biomedical research and the DoD. That's two really different application spaces. And we touched earlier on, the portability of methods between the two, but are you seeing any other cross-pollinations happening from where you sit? Things that you've learned over here with one group going, hey, over here, we believe this could apply as well with some adaptation or even directly. So are you seeing agencies across the government actually collaborating? No is an acceptable answer.
I see agencies collaborating when it's common. So for instance, we do a lot in the chem bio space in the government. And in the chem bio space, you have folks from DITRA, the Air Force, the Marines, who are all very interested in obviously keeping their warfighter out of the way of, a biological or chemical exposure and how to do net new identifications of substances and things. So they have a common goal and they will come together collaboratively at exercises, demonstrations, all sorts of things to say, how do we go and solve these problems? Same thing with ISR or other types of spaces. So I would say there is an air of collaboration, but in my opinion, like anything else, right, it's still incredibly siloed and there's too many people and too many things in programs and code words and classifications that anybody really can talk to each other and know what's going on. But again, I'm outside the wire, so my judgment's obviously biased. I think we're starting to see commonalities and frameworks being applied from the commercial space into the federal space, which is going to be important. When you look at a lot of the organizations like trade winds that they stand up, or the JAKE or whatever else, AALs or things like that, like there's a call for very strong outside commercial and academic partners in collaborations that, they will take somebody from Sloan Kettering that's doing X, Y, and I'm making up Sloan. I don't know if Sloan's involved in it, but Sloan X, Y, and Z to come in and say, well, what are you guys doing on the regulatory side for patient care and FDA approved devices? Because that looks very, very similar to what it means for me at the DoD to put AI in autonomy and give that to my warfighter, right? Because that systematic control, that change management, that regulatory process is so absurdly similar to if we gave a medical device to a patient and now a patient is using it to monitor their real-time vitals and life or death type of things. It's very similar. So that's where you start, in my opinion, to see a lot of this crossover, and frankly, why those are, well, there's a lot of reasons those are our two biggest industries, but you start to be able to really kind of cross understand the challenges in those two because they're very, very similar, and then use the learnings from each other to kind of bring and adapt, right?
Yeah, absolutely. So you've done a phenomenal job of sort of orienting us to where we started and how we got to where we are today. What do you see as next? Where do you see the evolution of AI capability evolving in the government? And what are the hard challenges for getting there?
So I think if we were to be honest with ourselves, the technology piece is highly solvable, and folks like you are solving it for us and making our lives very easy. The algorithm piece is also being highly solved by folks in academia who are then open sourcing a lot of these tools, and not just academia, in commercial space as well. You have folks like Facebook and Google and Tesla and folks open sourcing algorithms that then the entire community can use and solve, again, 99% of the problems out there. So from an algorithms, from an infrastructure perspective, there's really no excuse at this point. Like we got a good hold on it. You give me an ARI and a whole bunch of algorithms from Google, I could probably solve most of the problems in the world.
The process and the technology are there.
They're there. What's not there? So the easier of the not there is the data. The data, by and large, will be the biggest limiting factor in true deployable technology. If I want to enable a warfighter or even an analyst or even somebody that's just doing fraudulent claims for CMS, and I want them to go and do this across the entire US or to do this actually in the field, I need to make sure that the data that I give them will train an algorithm that's robust to their scenario. I don't think we're there yet. We're starting to see a lot of the space in simulation and data generation that's going to assist in that, omniverse, all that stuff, but we're still, that's not a solved problem yet, but it's solvable. I think the biggest challenge is the people problem. So people, in my opinion, are very hard to move because they are the ones that, for two reasons. One, most of the AI that we build by data scientists or whomever in a lab aren't the ones who need to inherently take the risk of using it. So think about the radiologist. I'm sitting in my computer, safe sound, nobody yelling at me. I'm writing a whole bunch of cool imaging things to find the next, I don't know, lesion in a lung scan. Okay. I now say, hey, surgeon, hey, radiologist, go use this because I'm 96% accurate. And I say, okay, that's cool. But if I use it and the patient dies, who owns that liability?
Right.
Who's going to tell that family that they died, that I used an algorithm? The association of risk to the person, the operator that is using it, is completely disconnected to all the cool tech and data and AI that we're doing. It's completely separated. Unless we combine that risk identification to the end user, the operator, to the kind of core people, we will always have a very large gap in actual adoption of technology. So that's one
criticality of outcome. What's the cost of being wrong?
It's the cost of being wrong, and we don't think about that because it's hard to think about, and it's dirty, right? It's dirty in the sense that, like, well, do we really want to think about the implications? And then the other part of the people problem is affecting and changing people is really hard. So now you have a lot of people who have done their jobs really, really well for a really long time. And you say, okay, now go do something different. go look over here, go learn this skill, go adopt this, go learn this new policy, start learning about deep learning algorithms and convolution. I say, I don't want to do any of that. Well, if we don't do it, then what does that mean? What are the outcome differences? So I think we have to upskill our people. We have to really think about how do we embed this as fundamental learnings early in our education cycle, way before they become professionals in high school and college, in their upskilling and everything like that. This is something that I know the Navy is very much focused on, is how do we give our soldiers that fundamental understanding and education such that when it is time for them to be out in the field, they actually understand the tech and they're using it, right? So there's that entire people process that we have to solve, both at the operator level and the education level, that I think is really the next paradigm for large scale adoption and use of AI.
It's funny, my parents always told me that I'd never make anything of myself playing all those video games all the time. But it wasn't the playing the video games was fun, but learning how to make them became something that drove me, and ultimately, voila, life and information technology. I agree with you. We've got to start helping people develop an enthusiasm and a skill set early on in the education, and I mean primary education, on why this is cool, why modeling an algorithm. I mean, it's going to start with intro to algebra, but it's got to be something that we start showcasing in primary education, so people are familiar with the concepts of how it works before they actually start delving into creating and extending the state of the art. And that's a huge challenge. I think that the DoD operates in a really interesting space in terms of being able to influence that at the collegiate level, for sure, with university affiliated research organizations, MIT, Johns Hopkins. There's a number, Georgia Tech Research Institute. So there's places where students can start leveraging the capability that's available at the university, or the capacity that's available at the university, to start developing expertise in these things. And I think that's incredibly powerful. The other challenge is, once you're really good at it, sadly, Google pays an awful lot of money.
A lot of money.
So it's how do you attract the talent and then give them a mission that a person really wants to believe in. And that's one of the things that's always filled me with wonder, is the sheer level of capability across the armed forces in terms of the people's skills that aren't on the books is breathtaking. So why do people with incredible capability do something that is not financially rewarding? And the answer has to be because it fulfills another personal need. And there's nothing like engineering like your life depends on it, because it does. That's exciting. We're always going to be challenged in government to compete with private industry, and the quality of life that comes with significantly higher paycheck. But in all the things that you've touched on, I don't think that anything makes more of a very personal life and death kind of impact than the types of things that the government engages in, whether it's the safety and security of us all, or improving our health, or education, or across every aspect of human endeavor. So I'm excited to see the growth of this technology and the growth of the knowledge base and the availability of people to perform the engineering necessary to create these capabilities. And really, it's the creating the capability. Using the capability becomes so transparently easy, people don't really often understand how much they interact with artificial intelligence every day.
That's right.
But I mean,
that's got to be the goal. Right.
As you said, the omniverse, the metaverse, Roblox, there's a whole bunch of AI in everybody's day that they don't even realize is actually already present. So it's going to be exciting to see the next 10 years. Right. When we look back on what the last 10 years built for us in terms of a jumping off point for exploring and exploiting this technology. So any parting thoughts, any observations or encouragements that you want to provide to our audience?
Sure. I can think of, let's see, off the top of my head. So I'm sure I've said this already, but the opportunities to utilize AI today is there, right? With what's already readily available at your fingertips, with some study. Don't be naive about it and just say, I'm going to download something and press play and hope that it works. But truly understanding it and then saying, okay, I want to get some infrastructure, I want to get some data, I want to get some algorithms. You can already start solving a significant amount of problem spaces out there that most likely will make you and your colleagues, and if you're supporting the warfighters or the analyst or whomever, significantly better or safer at their jobs. And there's really nothing stopping us from that, or from you from doing that today. So I think there's an incredible opportunity and responsibility of us in this community to really leverage what we've learned, kind of work together and make sure that we are doing it correctly, and in making sure that the people that are out there and kind of saving, the community, the world, our lives, and protecting us, we give them our best foot forward, because we should be, right? And that's our duty back to them. So my encouragement is, hey, if you're in this space, keep trucking on and make sure that you're collaborating and talking, because the lessons learned, it should be treated like a real scientific community where we're all learning from each other and growing. And I'm very proud and pleased to be a part of it. And obviously here with you, Nick, and doing this together. So if anybody ever wants to talk about it, problem spaces, successes, failures, work they want to do, reach out, and we can always just have that collaboration, because that's what we're here for.
Thank you, Michael. And we are very, very grateful for the partnership that we have with SFL and for all the support that you've given us. My typical way of describing this to people is I build cars and you build drivers. And we at Pure build infrastructure specifically for handling the challenges of massively parallel and massively scalable and massively concurrent data sets, because artificial intelligence training really brings together a lot of unusual aspects of data dynamics. But I can build the greatest car in the world. If there's nobody to drive it, doesn't matter. So we're really grateful that you've been able to show people how to leverage the tremendous computational capability that's at their disposal these days to get the outcomes that matter to them. And we look forward to continuing that collaboration for a long time in the future. I want to thank you for spending the time today with us and with the audience. I know you guys are incredibly busy over there at SFL, which is always a great problem to have. And we look forward to having you back again. So awesome. Thank you again.
Thank you, Nick.
And everybody, thank you for your time today. And we hope you enjoyed the Modern Data Experience, the ATARC Federal IT Newscast. And we look forward to seeing you next time.